We're running.
Okay. This particular problem that I'm talking about now covers several spheres of influence. The first of which being, I understand that in physics is hard. You guys tend to be rather bored by it. And so what this problem does is it livens things up a bit, makes things a little bit more interesting. This problem is similar to a cop in a car is chasing a bank robber in another car. How long does it take for them to meet and catch the robber? That's boring. That's unusual. I'm not into that. What this problem does is it conveys the idea that physics can be interesting, that we can solve many problems, and it does a little bit of, shall I say, social justice. Oh wow, how is that possible? Well, back in my day, there was Elvis was alive, and now he's dead. John Lennon was alive, and now he's dead. And Kurt Cobain is alive, and now he's dead. And yet there are some individuals who still live who have no talent. And that upsets me. So we're going to fix this. Picture, if you will, a green field. Beautiful blue skies. Sunny. It's a perfect day for breakfast. In the middle of the field, we have two cages. And the first thing you'd probably want to say is, well, what's the distance between the cages? And I'll say, and this is really the last time that we're going to use the metric system, I'm going to say that it's roughly 1.5 miles is the distance between the two. And so when you have, what's really going to happen is the cages will open, one will see the other, and the big question is, when and where is breakfast? So as I said before, so many popular music stars, true talents of our age, are dead. So in one of the cages, what I've done, I've placed Justin Bieber, because he is a talentless hack. Who said it? I said it. When did I say it? Right now. So, breakfast, when that cage opens, he's obviously going to do the right thing and just scoot this way. Because what's in this cage, shall we say, is ill-tempered and very hungry. So, in this particular cage, I give to you a Velociraptor. Now, those of you who have seen Jurassic Park, or Jurassic Park 1, 2, and Jurassic World and all that stuff, knows what I'm talking about. In this particular problem, he will run to the right, she will definitely run to the right, because she's got Bieber fever. And over here, breakfast will occur. So the big question is, when is this going to occur? Where is it going to occur? It's obviously going to occur to the right. Let us begin the problem solving. The first thing that you want to do with any problem is choose an origin. One. Origins, there can only be one, much like Heinrich did, for those of you who get the reference. I tend to pick the leftmost portion of the problem, so I tend to pick the cage where the Velociraptor is, which means that the initial position of the raptor is 0. I'll be using units of miles in this particular case. That means that Justin Bieber's coordinate will be 1.5 miles. The next thing I need to do is I need to give you a little bit more information about this. This is a simple problem. It illustrates simple points. One of the things that I will restrict this problem to is the idea that the Velociraptor's acceleration is 0 and the acceleration of Justin Bieber's velocity is also 0. This is to prevent, it adds a layer of complexity that I'm not prepared to address at this particular moment. So we won't have it. Next question. How fast do these things, or do these people, creatures, run? What do you think? And in this particular case, in the long semesters, the 14-week semesters, the first week we do estimation. Estimation problems are valuable because we're less interested in the numbers and more about the thought process that goes into the number. So the first question that I have is, what is, the cage is open and they instantly reach their maximum velocity. So we're simplifying it. We're not dealing with the fact that they're going to start from 0 and increase their velocity. You could say that they have a running start within the cage. What is the typical velocity in miles per hour of a pop star running? Full tilt with a Velociraptor behind it.
Like 7.
7 miles an hour? Now typically I could walk 3 miles an hour, so that's roughly twice. Usain Bolt can run like 25 for bursts. So and it doesn't really matter what the number is. Do we think that 7 is a good number? Or we had a couple of track athletes in the room and they were like, no way, I can run a lot faster than that. So is 7 a good number? Do people think it's higher than that? Are we fine with 7? Excellent. So 7 miles an hour. My guess is that number, see, with estimation problems, you say 7, and my opinion of that number is, it's a little low. No, I mean, it's not horrible. If you said 1 mile per hour, I'd be like, for an infant. So the numbers have to kind of make sense, but they don't. I'm more interested in the technique that we're using. This is going to be a fast chase. The Velociraptor's velocity, if you've ever seen the original Jurassic Park, they asked the park ranger, what kind of speed does a Velociraptor have? And he said, cheetah-like speed. Now, cheetahs have been known to go for a burst speed of like 90 miles an hour. We'll just use, trying to keep the numbers similar, 70 miles an hour. She's going to showboat it as she tracks him down. So we have the accelerations, we have the velocities. If the accelerations are 0, the initial velocity of the raptor is the same as the final velocity of the raptor, and the velocity of Justin Bieber will always be 7 miles per hour because there's no acceleration. If you got, what's the V equation? V equals V naught plus AT. If A is 0, V naught is equal to V. So in the generic, you just have that. So that's what you can say. So the velocity equations in this particular case are not that interesting. What is interesting is the position equations. Now, I'm not going to include the 1/2 AT squared. Acceleration is not relevant in this case. So we have this. Now we have 2 different equations. We have the position equation for the Velociraptor, and we have a position equation for Justin Bieber. So what is the important equation that we have, or that we can think of, which will say, where is breakfast? What is the equation that I have to use that says breakfast occurs here?
Would you set them equal to each other?
Not only would I will. Once again, you must, now here's an important lesson. I'm trying to encourage confidence. So let's say you were going to give a wrong answer. I prefer this over, would you set them equal to each other? No, that's wrong attitude, right answer. I prefer, you know what? Answer's elephant. Confident, but wrong, and appreciated. So I definitely encourage people to A, speak up, and if you give a wrong answer, I'm fine with it if you say it confidently. They are equal to each other. When the position of the Velociraptor equals that of Justin Bieber, we have breakfast. So XOR-VORT is equal to this. Now we've set our number line, we've defined the position as X. We've got the origin, we've identified that XR is equal to XJ. My next step, plug in my favorite number, 0. Which of these are 0?
X naught of the raptor.
X naught of the raptor, correct. So that goes to 0. Now, get my red pen and my green pen. I know what V naught R is. I know what X naught J is. I know what V naught J is. But I don't know what time is. We have a one equation, one unknown. We're able to solve this. We may now proceed. Here, one thing, rule of advice for tests and for problem sets. One of the most annoying things that a professor can say is, well, it can be easily shown that, and then just write the answer down. And you're like, no, it can't be easily shown. This is my second day. I don't know any of this. So one of the things that I have to do, and I respect your desire, is I have to show all the steps. I expect the same in return on the test. Do not skip steps. Now, there's some where you could do like 2 or 3 algebraic manipulations in the same thing. A lot of them are kind of easy. But for here, I have to do this painfully slow. Why? It's your second day. Here over here. And I get this. All I did was subtract this from both sides. Next, factor out t. And then solve for t. Dividing both sides by that segment. And that's the time. I know what x naught j is. I know what the 2 velocities are. I'm good to go with this. One of the things that we have to do, and this is a good lesson to cover right now, is you look at this and go, I'm not sure if this is the right equation. I don't believe that it is. I'm going to double check. When in doubt, unit check. Check your units. On the left, we have time. What is the common unit of time? Seconds. Now, you could use Seconds, minutes, hours, it doesn't matter as long as you use the same unit for all instances of time. If you've got a distance, you could use meters, miles, anything like that, as long as it's the same type of unit. X, we could use miles. And in fact, let's use the units that were given just for less confusion. Miles is X. V naught R is miles per hour. Miles per hour. Miles per hour minus miles per hour will give you miles per hour. And then you have this. This is in the numerator, that's in the denominator, that's in the denominator of the denominator. Those cancel, and you're left with hours. This is a very simple example, but it shows a technique that if you master, when you deal with far more complex equations, it's going to help you immensely. Because if you got an equation and you've got hours on one side and you've got hours per mile on the other, you've messed up. So now we have time. Our distance, 1.5, V naught R, 70, his is 7, so it's 1.5 divided by 63. 0.0238 hours. Or you could say 2.38 times 10 to the negative 2. That really doesn't make too much sense. So what I'm going to do is I'm going to multiply it by 60 minutes per hour, 60 seconds per minute. So that's 0.0238. I got the number in my computer, multiplied by 3,600. 85.7 seconds. You could barely get to the chorus line in any of his lame songs in 85.7 seconds. Now, that's the time. That's a sensible time. I would accept this, but this is something that we could wrap our mind around. If I said what's 0.0238 hours, I wouldn't know. 85.7, I can figure that out. Where is it going to occur? Well, now you're flexible. You could pick either equation. Both are going to give you the same answer because you set the criteria that they both equal at breakfast. I'm going to use Justin Bieber's position. Now V naught J is 7. The time, the velocity is in miles per hour. That's in miles. This has to be, the time has to be in hours. So we're going to use 0.0238. And that will give me 1 2/3. Now that's the coordinate. If the final coordinate is 1.67 miles, is that 1.67 miles to the right of the Velociraptor cage or Justin Bieber's cage? The Velociraptor, because we used the Velociraptor's cage as the origin. So if I ask how far to the right did breakfast occur from Justin Bieber's cage, all you would need to do is take the coordinates between the two, because displacement is just the final position minus the initial position, and you get 0.17 miles. So it's 0.17 miles to the right of Justin's cage, 1.67 to the right of the Velociraptor's cage. It took 85.7 seconds to do. And so that's the Justin Bieber problem. It's very simple. It illustrates one-dimensional motion technique. I think it conveys to the student when Dr. Eschenberg says or does any stranger things than this. It's perfectly understandable because I kill pop stars with Velociraptors. So. One. Now what we've done is we've touched on one-dimensional motion, and for the next hour or so we're going to have to get a little bit mathy. The plan is for the next hour or so we're going to do vectors and vector addition. And a little bit after that, we're going to do two-dimensional motion, and two-dimensional motion will help you with your 1D motion problems that you've been assigned. Vectors, vectors, vectors. It is all about vectors. Part of me is kind of insulted that the math department does not teach about vectors until Cal 4. Like, they don't even consider it, they consider it too hard until you've had at least 3 semesters of math. You can learn a lot about vectors immediately. You guys are never going to have Cal for the most part, so let's just learn it. Vectors, when you see a vector, it will look like an arrow, and it'll have a magnitude and a direction. It could go in all sorts of different directions. There's something else called scalars. Scalars are magnitude only. Scalars are typically, you just draw the letter M or for mass, or Q for charge, which we'll cover in 214. It just has a magnitude. Vectors have magnitude and direction. So whereas a scalar just says, scalar, 62 people. That's a scalar. That's a magnitude only. Vectors look like 3 meters per second at 80 degrees. Scalars look like 3x hat minus 2y hat meters per second. Those are descriptions of vectors. Whereas scalar, you just have a letter. A vector you have the vector symbol. It looks like an arrow, but the lower branch of the arrow has been erased. So if you see this, you know you're dealing with a vector. If you just see something without the hat symbol, or not the hat symbol, but that, you're dealing with the magnitude. Vectors come in 2 forms. Component notation and polar notation. Polar notation, I've written both forms over there. The example is 3 meters per second at 80 degrees. This could be simplified to x, some sort of unit, at theta degrees. When you see something like x blah at theta degrees, you're dealing with a polar notation vector. When you're looking at a component vector, you're looking at something like this. You see an X with a little symbol on top. We call it a hat. You got a Y with a little hat. You got some numbers out front, and then the units bringing up the rear outside the parentheses. That is a component notation vector, or a component vector. As I've said, this deals with theta. It's an angle. The angles always start from here. And then they always move counterclockwise. So when I say 80 degrees, you start here and you go counterclockwise. If theta is less than 0, you rotate clockwise. So 80 degrees is counterclockwise by 80. Clockwise, negative 80 degrees, you would start here and go down, like that. For component notation, and we'll start with this first. Well, we've already started. For this, X hat and Y hat are both unit vectors. Unit vectors are something that we can talk about in this way. We're going to have an oversimplification of Oxford and Ole Miss geography. If here is the Lyceum, and over here is the square. And I said, how do I get to the square? You go, well, that's easy. You just take University down to South Lamar, turn left, and go about 3 blocks, and then you're right there. Well, how far from the Lyceum to that turn? It's about 15, let's just say. So you travel 15 blocks east, and then go 3 blocks north. Now, we can change this into a component vector. We could say that our directions, A, is positive 15 east, or really 15 east, plus 3 north blocks. This is a component vector. You travel 15 blocks to the east, you travel 3 blocks to the north, and you get it. Also, you could rewrite it like this. You could say 3 north plus 15 east blocks oversimplifying it to, you go 3 blocks north to West Jackson, and then 15 blocks east to the square. Now, in both cases, they get you to the same place. The order of the vectors do not matter. There's also, these vectors can be expressed as a polar vector. If this is 15 and that's 3, this length here, you use Pythagorean theorem. 15 squared plus 3 squared, square root of 234, whatever that is. 15.3. So you could either go 15 blocks east and 3 blocks north, or travel in this direction by 15.3 blocks, whatever the length of a block is. To get this theta, we know that tangent of theta is y over x, and I'm about to do a rant about your trig teachers. Tangent theta is y over x. Theta is inverse tan of 3 over 15. So that theta $11.3. So 3 blocks north and 15 blocks east, 15 blocks east and 3 north is the same as 15.3 blocks at 11.3 degrees. So what we have done is a simple conversion from a component vector to a polar vector. It is a skill that you must have. Convert component to polar. Now, one of the other things that I've shown in this simple demonstration is tip to tail method and parallelogram method. In the tip to tail method, if you have any two vectors, like what we had here, you go one vector, you go another vector, and then you go, see, this is the tip of one vector, that's the tail of the next. And the resulting vector, you start at the tail of the first vector and end up at the tip of the next. That's the classic tip to tail method. In the parallelogram method, it's what we've shown in black and red. In the parallelogram method, you take your two vectors and you reorder them, and you end up in the same direction. In the parallelogram method, this basically shows that the two vectors you're adding, which is what we're going to do, you could go that vector first and that second, or that vector first and then that vector second. It doesn't matter. It's going to end up in the same place. And so that's a simple version of the parallelogram method. That's tip to tail. Typically in a parallelogram method, you do like these weird angles. And granted, I'm just doing this not on graph paper. But in the end, you use the parallelogram method, those vectors should line up to be close to each other. Now, on to the rant about your trig teacher. So I kind of just power memorized it. And what I found is a lot of your teachers are just horrible. And they're horrible because I will catch someone in this room eventually who sits there and goes, well, this is your triangle, that's y, that's x, that's theta, that's the hypotenuse, and so sine of theta is y over hypotenuse, and cosine theta is x over hypotenuse, and then they just memorize that. This is, for this particular case, technically correct. But what if I didn't give you this angle, but I gave you that angle? In this particular case, sine of theta is not equal to, well, it's not equal to y over h, and cosine theta is not equal to x over h. By definition, sine of an angle is the opposite side length divided by the hypotenuse. Cosine theta is the adjacent side divided by hypotenuse, and tan theta is opposite divided by adjacent. These are the true definitions. That is just a specific case. If I said, well, what's sine of theta? This theta, and you said y over h, I know that you were academically abused as a child by your trig teacher because they didn't show you the true definition. Who does know the true definition? Brenda from Beverly Hills of 90210. I'm sitting there, I'm grading papers. There's an episode where she's teaching some trig student. She's a senior, kid's like a freshman, and she tells him about Chief Sokotoa. And this is the mnemonic. There are all sorts of mnemonics. So, sine opposite hypotenuse, cosine adjacent hypotenuse, toa, tan opposite over adjacent. And I looked up and I said, oh my God, Beverly Hills 90210 has taught me trig. These are the true definitions. These are what you should memorize, not this. These will be what you really need. What we're really building towards is, I'll kind of write it out right now. For test 1, I will put this up, the old test's up, I'm not afraid of it. You will have 25 multiple choice. We'll take a look at that over the 2 review days. You have an appetizer problem, which is a conversion problem. And then you have 3 problems. 1 will be an Atwood's machine problem, which we have not covered yet. We'll cover that tomorrow. 2 is a 2D motion problem. We'll cover that at the end of this lecture and tomorrow as well. And problem 1, vector addition. You will be given 2 vectors, and I want you to add them up. That's the test. I've been giving this test for like 6 years now, and they haven't figured it out. First, unlike a lot of other professors, I don't lie. This is going to be on the test. A lot of students go, well, if he said that, he's not going to put it on the test. It's going to be on the test. This particular problem, Atwood's machine, there's a whole story to that. I will cover it in detail later. But the vector addition problem, if you don't know how to add vectors, you've got issues. Because when we do collision problems, we're going to be adding momentum vectors. When we're doing circular motion, we've got radial acceleration vectors, velocity vectors. When you've got a charged particle moving in a magnetic field, there are vectors all over the place. If you don't know how to do simple vector addition, it's going to be a long, hard slog. So, let's talk about vectors. We're all familiar with this. The axes. The x-axis and the y-axis. Now, if I said, think about just the coordinate system. X is to the right, positive x is to the right, positive y is up. That means negative y is down and positive x, or I'm sorry, negative x is to the left. So if I gave you the coordinates 3, 2, what does that mean? 3, 2, x coordinate first, y coordinate second. So you'd go 1, 2, 3, 1, 2, and the coordinate that I'm talking about is right there. Well, question. What quadrant is that point in? Well, quadrants, and I'll only write it once. You have the first quadrant, second quadrant, third quadrant, fourth quadrant. Going counterclockwise once again. Another way of writing this, I'll either write first, second, third, or fourth, or I'll write the Roman numeral. And you get this. What's the thing that you know about the x and y coordinates for a first quadrant coordinate? They're both positive, exactly. So if you hear me say it's the quadrant that's positive, positive, you know it's a first quadrant point or vector. You know first quadrant is what? Up and to the right. For a second quadrant, the coordinates is x positive or negative? Negative. Is y positive or negative? Positive. And one of the things that we'll start to learn is when I'm doing all of these rapid fire questions, you're basically hearing multiple choice questions. Third quadrant, will it be positive, negative? No, it'll be negative, negative. Correct. And that leaves us with fourth quadrant, x is, y is, excellent. So those are the quadrants. Those are the associated signs for coordinates. And if you have vectors that go in these directions, an example of a first quadrant vector is something like positive 3 x hat plus 2 y hat meters. Both components are positive. This is the x component. That is the y component. For a component vector, component vectors are typically written like this. This is the generic form. AX and AY are your components. AX is associated with X hat, Y is associated with Y hat. If I had to draw an X hat vector, it is length 1 and pure positive X direction. If I had Y hat, it is length 1 pure positive Y direction. So if we needed a vector that went down, the component would be negative. If we need an X part that's to the left, that would be negative. Yes?
What do you mean by pure?
Pure as in and this is probably in my own usage. Pure vector, it only goes along the axes. And one of the things that you did is that you just shouted out a question, which is entirely appreciated. Why? Because if you ask that question, there are 20, 30 people asking the same thing. Now, if you run on your mouth like 20, 30 questions, then I'll be like, all right, let's just tone it down. But that was appropriate. Axes. Another thing that we know, I don't care about spelling. If you want to know how to spell, go over to Bondurant or something. I don't know. So, these are the component vectors. You've got X component, Y component. If it's going up, you know your AY is positive. If it's going down, you know your AY is negative. For the other quadrants, and a sample of a second quadrant would be negative 3x hat plus 2y hat meters. Quadrant 3, negative 3x hat minus 2y hat meters. And so that would be another example of a fourth quadrant vector. So if you're looking at a vector and you see this, positive x, negative y, your first instinct is, it is fourth quadrant. Done. There's a lot of this that should become muscle memory. Now that just deals with the components. For polar, we have quadrant 1, 2, 3, and 4. Now, here are our 4 vectors.
I'm going to redraw these. 1, 2, 3, and 4.
So, first quadrant, second quadrant, third quadrant, fourth quadrant for the vector. So in one case, the vector is going up and to the right, the next upper to the left, third lower left, fourth lower right. We need to introduce the idea of absolute angle. Now, occasionally I will write it, shorten it like that. This is the symbol for angle. Always starts at positive x axis and rotates counterclockwise. So for the 4 quadrant vectors in red are my absolute angles. And how I label them when I'm just referring to them as an absolute angle is theta A. Now, how many degrees in a right angle? 90. How many degrees in a full circle? 360. So if I give you a first quadrant vector, theta A should be between what 2 angles? 0 and 90. If I give you a second quadrant vector, your angles should be between what? 90 and 180. If I give you a third quadrant vector, the absolute angle should be between what 2 numbers? 180 and 270. Yes, good. If I give you a fourth quadrant, what 2 numbers? 270 and 360. For the test, for your problem sets, when I go, give me this angle as an absolute angle, the number must be between 0 and 360. It cannot be 450. If you've got an angle greater than 360, before you start playing with it, if I gave you 450, just keep deducting 360 from it until you get a number that is between 360 and 0. A couple of these problems are on the problem set. When you're adding these vectors, there are 7 vector addition problems. The first 5, I'm being a little bit tricky, just seeing if you're paying attention. The last 2 are power vector addition problems. It's just to grind through it. The vector addition problem set is a long slog of just math and repetition. Also, just as a note, I'll send the link just to be sure. Look my name up on YouTube. These problem sets are the same problem sets that I gave in the spring. So you can either find somebody who has the notes or go through my YouTube channel, look around January 28th or early February. Look for the word tutorial or TUT, T-U-T. The file name occasionally ends in T-U-T. In there, and this is my personal philosophy, homework's only 10%. It's not that big of a deal. I need you to do the practice work. Practice, 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 always practice. And what I do in these tutorials is I do the homework. if you gain access, and I'll do it today. I'll give you access to the full video library of all that I've done. Look for the first tutorial mentioned in a 213 directory, and that typically is unit conversions and 1D motion. Particularly, and there will be a mention of Super Monkey, that particular problem, and it's not the Snooki problem. We don't want to make an orphan. The Taylor Swift drop problem. That, if you understand those two, you can really go through it. And I go through those problems in the tutorial. There's no need to talk to me. You can just look at the video. Back to this. So if I say 75 degrees, what quadrant? First quadrant. Is y negative in that case? No. What is it? It's positive. So you've got to be able to like quickly associate if you guys aren't saved. If x is negative and y is positive, and I give you an absolute angle of 220 degrees, is that right or wrong?
Wrong.
It's wrong. What's wrong about
It would be in the third
it?
quadrant.
It would be in the third quadrant. Excellent. So you've got to have that instinctual ability to be able to look at vectors and translate them. I use, I'll get rid of this. In physics, there are dozens of ways to do all sorts of problems. After teaching, this is I think it's my 21st time to teach 213 in a semester. I've taught it a lot. What I've been able to do is sand down and polish my teaching style and get it to a situation where the system I'm about to teach you, in my opinion, is the best because I think it most efficiently teaches you. It's the best way to easily learn what's going on. And I call it, well, I don't call it green. The reference angle system. The reference angle is marked in green, and they're listed as theta r. Now, the one thing that you do notice with these angles is that regardless of the quadrant, the reference angles always go up or down from x-axis. And really, I hate writing words on the board. When I'm writing words, it's some important stuff. When working with the math of these problems, we're going to let logic prevail and let our brain decide positive and negative. if we do the math and we end up in a second quadrant where our x is positive, we've messed up. The way that I do these is I use my reference angles, I use magnitudes, and when I put the stuff together finally, that's when I put in the signs. I do not let the calculator tell me about the signs. I'm the one telling the calculator what signs to use. Oh, the relationship between these things. In a first quadrant, the reference angle is equal to the absolute angle. In a second quadrant angle, the sum is equal to 180. In this particular case, 180 plus theta r is equal to theta a. Or you could say that theta r is equal to theta a minus 180. So you can manipulate all these equations to go from a reference angle to an absolute angle. For fourth quadrant, 360 minus theta r is equal to theta a. So if you're doing a fourth quadrant vector, you use this equation, not this. If you've got a second quadrant equation or second quadrant vector, you don't use this, you use this. Now, what I've done is I've set up the fundamental theory for vector addition. For vector addition, which all of you will have to do on the test and on homework, and most likely the final. So for vector addition, an example that we'll work with is you've got 3 meters at 180 degrees, and that is my A vector. You've got four meters at 300 degrees, and that is your B vector. What is the resultant C vector if C is equal to A plus B? And what is the equilibrant D vector? And we'll go over this right now. So if you know how to do this, if you look at this and go, well, that's no big deal, and crank it out in 5 minutes, you got one of the major problems ready to go on the test. Now, just so you know, first time I ever taught summer school, for test 1, I thought it would be a great idea. Get ahead of the game. In the first hour, we'd have the test, and in the second hour, I would give a lecture. How do we think that turned out? For the second hour, I had a whole bunch of people just looking at me going, I hate you. So, since then, what I have done is this. You've got an advantage. Now, granted, you have the penalty of you're covering a month's worth of physics in 7 days. But in return, what I do is I write a test that is typical for my normal hour, 15-minute classes. And then I give you the full hour 50. Because I know your brain's not ready for anything after that test. So the test, I give you a heavy additional time to work with it. So don't worry about doing anything else after the test other than maybe laugh. But for vector addition, what we're doing is, if we want to draw it, 3 meters at 180 degrees is like this. 1, 2, 3. So this is my A vector. The B vector, we use the tip to tail method. It's as if you draw a small origin here, and then you go 4 meters at 300 degrees from here. So you draw 4 like that. Now, this is just a ballpark idea. So the resultant C looks like that. I'm not sure of the exact angle, but what I do know is that the resultant, or C, should be in the 270 degree neighborhood. It should have a very small X component and a very big or a normal sized Y component. If we do the parallelogram method, we do this. And then we draw our little origin here, and then we go 1, 2, 3 in a pure negative y hat direction, or negative x hat direction. This is basically what you're doing. Today, you're doing 1D motion. Tomorrow, if there is lab, I think you guys have lab, you're doing vector addition. You're just doing a whole bunch of this. So ideally, it should be down and to the right. Or if it's down and to the left, that's fine. This is just handwritten. One of you may ask, well, what's the equilibrium? The equilibrium cancels the resultant. C is equal to, well, actually what I'll do is I'll draw it like this. D is equal to negative C, or D plus C is equal to 0. It balances it out. An example of which is where C goes down and to the right, D goes up and to the left. Now let's talk about vector addition. Vector addition comes in 3 steps. You break them. You add them. And you recombine. Those are the 3 fundamental steps of vector addition. A little bit more in detail. Break them, convert polar to component. Add them. Add component parts. X's to X's, Y's to Y's. And then you recombine. The recombine part means convert component to polar. Now typically when we do these vector addition problems, when we grade them, all the grader really does is they look at the polar vector that you give as your resultant. And if it's within a few degrees and the magnitude's within a few meters, or within a few fraction of a meter, then we know you did it right. If you get a weird answer, then we know you did it wrong, and then we start investigating. In these vector addition problems that I give you, to save time, problems 6 and 7 on problem set 2 are just power addition. In the test, one of these vectors will be an instant conversion vector. A or B will be a vector that you can just look at and go, no math is needed, I can just change it. Instant vectors, or instant conversion vectors, their thetas are always multiples of 90. 0, 90, 180, 270. So the instant conversion vector is A. 3 meters at 180 degrees does not require math. All you're doing, if you're trying to use a calculator to change 3 meters at 180 degrees, is waste time. 3 meters at 180 degrees is what in component notation? And it should take like that.
-3, 0.
-3, finish the statement.
Comma 0. Y
Comma 0? No, it's on the x-axis. So it's what? Fix it. You got so close and then it fell away. So it's in the negative x direction. So it's -3 x hat. Done. So the 3 meters at 180 goes immediately to -3 x hat. So if I said 3 meters at 0 degrees, that's 3x hat. If I said 3 meters at, 3y hat, that's 3 meters at 90 degrees. If I say 3 meters at 270 degrees, you say -3y hat. It's that fast. If you're sitting there with a calculator, I know you're not really working it right. Now, for B is a little bit more of a problem. For B, what I tend to do is I draw it out. And I draw a generic, B is a 4th quadrant vector. Now granted, some of you may say, well, it's over there on the left-hand side. Why is it not a 2nd or a 3rd quadrant? Vectors are not based on location. They are based on direction and magnitude. So what you do is you look at the 4 meters at 300 and you go, well, that's 4th quadrant. And you draw a 4th quadrant arrow. And then what you do is you draw X component and Y. And what I'm drawing right now is choosing of a notation right now to avoid, I'll use lowercase b. Bx is the absolute value of bx, and by is the absolute value of by. I like to figure things out by using magnitudes. The absolute angle that's 300 degrees. This, for the 4th quadrant, is your reference angle. Your reference angle is 360 minus theta absolute. 360 minus 300, and that gives you 60 degrees. And that is your reference angle for this 4th quadrant vector. using this as my angle, by is my opposite side, bx is my adjacent side, so sine of theta r is by over b. B is just the magnitude. Cosine theta r is bx over b. So bx, b cosine theta, said 4 cosine 60. One of the fun things, cosine 60 is the same as sine of 30. It's 0.5. So that's 2. By is b sine theta r, or 4 sine 60. .64. And those are the magnitudes of that vector. We have broken down the vector. What we're going to do is the second step. A vector is negative 3x hat. The B vector, what I'm going to do now is write it as 2x hat 3.64 y hat. And actually, we can look at this and say, all right, it's going to be third quadrant. Let me ask you a question. Earlier, I said we will let our logic determine the signs. The way that I do this with the reference and the magnitude system is that if you always go down or up from your x component or from your x axes, these will always hold true. If you have this, and I sometimes mention it as the vector butterfly, if you're always going up or down from the positive x-axis and likewise for the negative x-axis, you will always get these relationships. You always find the magnitudes. Now, some people say, well, I'm going to let the calculator determine the signs. Well, that's great, but that's just playing with the calculator. I want you guys to understand it. So that's why I require using magnitude. I know that B is down and to the right. B is a fourth quadrant vector. So what's the sign on the x component for a fourth quadrant vector? Positive. So I put a positive here, not because the calculator told me, because I knew. What sign goes there? Negative. So what happens is, I'm happy now. You add negative 3 to positive 2, which leaves you with a negative x hat. 0 minus 3.64 is minus 3.64 y hat meters, and that is C. That is the resultant. You add your x's and x's, y's to y's. You do not add that to that. You have to keep, like Ghostbusters, don't cross the street, except at the very end. But even in that case, for a vector, that's bad. You now have this. This is your resultant in component notation. The equilibrant, all you have to do is flip signs. Negatives become positive, positives become negative, and so this is the equilibrant vector for this problem. So we're already half done with getting answers. So we've done parts 1 and 2 for the equilibrant and the resultant. The last part, the recombine, convert the components to polar, is this. Now, looking at C, what quadrant vector am I dealing with? What quadrant is C? It's third. Why? Because it's got negative, negative. If it's negative, negative, it's obviously a third quadrant. What should my absolute angle be? Between what range? Between 180 and 270. Trick question. What range should my reference angle be? 0 and 90. Reference angle is always between 0 and 90, regardless of quadrant. So we're dealing with now a third quadrant vector. Draw a generic third quadrant vector. Once again, Cx, then Cy, and then the big C. The big C, or the magnitude of the C vector, is just Cx squared plus Cy squared. Cx is 1. Cy, I don't care about signs right now because I'm squaring them. And I get that. Square root of 13, 3.6. 3.61 or whatever, 3.6 is fine. So that's the magnitude of C. This is my reference angle. I always drop from the x-axis when it's a third quadrant vector. Inverse tan of opposite over adjacent will give me that reference angle. So my reference angle is the inverse tan of Cy 3.64 over 1. So the inverse tan of 3.64. $74.6. That's my reference angle. It's a third quadrant vector. Therefore, absolute is equal to 180 plus reference, because absolute minus 180 is reference. So this gives me 180 plus 74.6, which means I have 254.6 degrees. And that is the absolute angle. So my C vector, answer, 3.6 meters at 254.6 degrees. And that's the resultant. Typically on the test, we only look for a resultant. In your lab, you need to use the equilibrium in order for this equipment to work. To get theta sub d, the angle for the equilibrium, you take that absolute angle minus 180 if theta A is greater than 180, or it's theta A plus 180 if theta A is less than. So in this particular case, our theta A is greater than 180, so theta D is 254.6 minus 180. Now granted, it brings us back to 74.6 degrees. It's not always the reference angle It's just that for a third quadrant, it's coincidental. So D has the same magnitude, 3.6 meters at 74.6. And so that's a vector addition problem. If you look at the tutorials and the videos, the lecture videos, I do all sorts of vector addition problems. In fact, you could probably look at the test 1 review videos, and I do vector addition in them. There are dozens of examples that I've done. This outlines the general format of a vector addition problem. And so we've got 6 days to master it before the test. So, the last thing that we're going to touch on is 2D motion, and it has a review of one D motion with 1D motion there's all sorts of stuff. When you have a one-dimensional motion problem, all you do is immediately reach into your toolkit not you. You. You write those two equations down. You see a one-dimensional motion problem, that's what you do. And then you look at the situation of label, origin, and your axes plus and minus. You write out the basic equations. You plug in zeros to simplify. You ID quantities that you know and don't know. So you label the origin and you say, well, where's plus and where's minus? You write out the basic equations. Then you plug in my favorite number 0 to simplify things. And then you ID the quantities that you know, which I typically label by a green line and don't know by a red line. One of two things will happen. One equation will only have one unknown. If that's so, attack that first. You attack the weakest part of the problem first. Second, it could be two equations, two unknowns. There's a great tweet by one of my students. She said, every time Dr. Eschenberg says two equations, two unknowns, I die a little more inside. It's not that bad. you could write all sorts of two equations, two unknowns. A minus B equals 4. 2A plus B equals -2. That's a two equation, two unknown. What do? We solve for one. A equals 4 plus B. What's the next step? Plug it into the other. 2, 4 plus B is equal to -2. I took that and plugged it in there. Now I have an equation existing only of B. 8 plus 2B plus B is equal to -2. This is 3B. 8 comes over -10, so B is equal to -10/3. And then all you do now is plug that into there. 4 minus 10/3, which I believe is 2/3. And so now we've solved it. Two equation, two unknown. It's not that big of a deal. You will get one of these on your math test in lab. So that's just the general procedure. This, what I've written right here, is not only applicable for 1D motion, it is applicable for 2D motion, it is applicable for rotation problems, it is applicable for all sorts of things. You understand these 5 steps, 213 is going to be easy. You just have to have a willingness to stay on the path, not panic, practice a lot, do a lot of repetition, and the whole thing will fall into place. For 2D motion, for 2D motion, 1D motion, you immediately get the x position equation and the velocity equation. You write those down. For 2D motion, what is typically done is you write this and you write this. Now, these two are the primary equations. When you're doing the problems, these 2D motion, and in fact, the way that I've written it, technically, there should be a 1/2 AT squared here, but what we're going to do today is deal with ballistics. Motion under gravity influence only. Throwing a football, throwing a baseball, dropping a brick off a roof, kicking a soccer ball, all sorts of stuff follows these types of equations. The primary 2 equations you write out are those 2. The next 2 are these. Typically, the way that the ballistics problems, the 2D motion problems work out is that you need these 2 to work things through, and then the extra questions use these. Now, one can ask, where's the A for the x coordinates? So let me demonstrate, and then I'll let you guys observe. This is why there is no A in the x equation. Did I shift from left to right? No. Gravity, as far as we're concerned in in the 213 case, gravity only acts in the vertical. Now granted, when you really think about it, try not to because it fries your brain, we're just little specks on a big ball in space. So really, technically, we're on just a big sphere. But as far as we can tell, just by looking around, we're really on a flat surface. And so we're going to approximate gravity of a planet to just a force that pulls down. So AX does not exist. A in our case will be negative G. G in my world is the magnitude of gravity. Now in 223, A is 9.8 or negative 9.81 meters per second squared. I used to be a gravity zealot back in high school, and I said, it's only negative 9.81, only. But in whiteboard, so down the hall in 223, the gravity that you use is 9.8 or 9.81, I don't mind. Here, we're going to use negative 10. And why is that? Because it's just so easily divisible by 2. It just makes things easier. I'm not interested in the numbers, I'm interested in the technique that you use. So by using 10, I'm kind of thumbing my nose at all my zealot self back when I was like 18. When you've got this, let's just throw out an example. You have a ball, and you launch it off the side of a cliff. Now, this cliff, you launch it up at an angle of inclination, and you don't know what that is, and V0 is an unknown. But what I have to give you is the following. I'm going to give you the height of that cliff, which I'll say is 200 meters. And then I'm going to give you that the time of flight is equal to 12 seconds. And I think I need to give you this. If I don't, actually, I know what I'm going to do. I'm going to change it. I'm going to change it to 30 degrees. I'm going to give you the angle. So I give you the angle of inclination, but I don't know the velocity. I do know that the time of flight is 12 seconds, but I don't know that distance. So I think that will be enough. So my two unknowns are the distance from the base of the cliff and the initial velocity of the ball. What's the first thing we do? We write out our two equations. X equals x0 plus v0 x t, and y equals y0 plus v0 y t plus 1/2 a t squared. It's the first thing you do. Though technically the first thing that you really do, 4 minutes, is you label your origin. I picked the lower leftmost part of the problem. I picked the base of the cliff. Now to speed things up a bit, that means x0 is 0. The initial x position is directly underneath the launch point. That's 0. Y final is 0. Y initial is going to be 200. Because we're dealing with a launch situation, theta, v0 y, v0 x, v0 cosine theta, v0 y, v0 sine theta. So x is equal to v0 cosine theta, t, 0 equals y naught plus v naught sine theta t plus 1/2 a t squared. 3 minutes. ID what you know and don't know. Only thing I don't know is x, and I don't know v naught. But I do know y naught, theta, a, and t. In this particular case, this is one equation, two unknowns, x and v naught. In this equation, it is one equation, one unknown. We attack that first. 2 minutes. Minus 1/2 at squared minus y naught is v naught sine theta t. I'm looking for v naught, so this is minus 1/2 at squared minus y naught divided by t sine theta is v naught. And so what I'm going to do is describe what we need to do for the rest of the problem. I have this expression for v naught. Plug everything in, you got v naught. That makes v naught over here a known quantity. Take that v naught that you just solved for, plug it in here, and you've got it. What I'll do is I'm going to take a photo of this, spend 2-3 minutes working out the numbers, and then I'll send you the answers online. That's it. Have a good day.